So I want to talk about a few things and showcase a few things overall in this particular video. The bottom line, like the first thing that I want to talk about is that if you think that there's like any money at all involved in physics, like even like big breakthroughs with physics, right? You're sorely mistaken. Like physicists aren't rolling around in money. They're not like millionaires, right? Even the ones that do like big things, they're not like just rolling in cash. And the reason is it's hard to find, first of all, commercially viable interests, and then secondarily, even if you have commercially viable interests, it's hard to prove it, right? Like, okay, I mean, I've shown you on this channel multiple times what I'm about to show you now, but like I'll show it to you in this instance, in a new instance, and in a new light, right? So this is another lossless compression algorithm. 30% compress. I mean, we're going to get 30% lossless compression. If you look at Kaggle, you go to the experiments right now. Like, there's a Kaggle competition right now for $20,000 for exactly what I'm going to show you, right? And then the problem with that is that you jump through a bunch of hoops for that. Then you're turning over the algorithm to them, et cetera. Like there's a whole bunch of hoops and understanding and all of that hoopla for $20,000, and then they're going to take that and they're going to sell it to their commercial interest for a lot more than $20,000, right? And then so pointing that out, like those are the reasons why I don't want to go for those particular routes. Like I would rather have one buyer overall for compression. And again, to me, compression is like I have kids, right? I need to eat, and I like food. So we live in a capitalist society. I didn't do it. And then overall within that, the smallest sliver of this that I can possibly carve out is compression. It's the one area that companies care about far more than individuals, and it has a far bigger impact on a enterprise organization, and it has like almost zero impact on your everyday life as an individual consumer. And then so within that, it's the one area of this that I can carve out. And then so secondary, like the second thing is if you want to like make some sort of like fresh comment that like I'm showing this on YouTube and then you can reconstruct it, sure. Yeah, I'm going to show you this algorithm here via YouTube. If you can reconstruct this algorithm and how we solve for the Riemannian hypothesis, and then as well as how we apply that to eigenvalues via this, and you understand exactly what I just talked about, and you can reconstruct it via this code that I'm showing here, like you deserve it, right? So you can go do that. But so bottom line that I want to showcase here in this particular example is the actual results. And then so as you can see here, it's my uncompressed file is 4,000 bytes. I compress it down to 2,828 bytes, which is over 30% compression. And then as you can see, 0% loss as far as reconstruction. Again, the Kaggle competition is for 20% loss, 20% lossless. I'm showing you right here, 30% lossless. Flat out, this is $20,000, right? It's for hoops to jump through it. For anyone that would want to go through that particular process. Like I've seen the Kaggle competition, it's live, and 20%, here's 30%. So overall, there you go within that, right? Again, it's I'm not interested in that low level thing. If you understand exactly what I'm showcasing here and you want to particularly or potentially buy this, then feel free to reach out. We want one buyer to rule them all when it comes to compression, right? I'm not trying to play like games or like I'm going to license this out. No, like I want one buyer flat out, period. If you want me to stop working on compression after that, I would assume that would be part of the agreement. Sure, no problem. But whatever you want to work out, let's talk. And then so within that, what I will showcase to you and give to you as a result of this particular video, because I do like to give code, right? So I'm going to give you a bunch of code here. And then what I'm going to give you is, this is an experiment that we run, that I ran recently on artificial entanglement, right? And then so you might be asking yourself, like, how exactly, and people have asked, how exactly is it that we're doing these things, right? And I can't state it enough. It comes down to physics and understanding physics. And then so to me, when I looked at this whole entire market, whole entire industry 3 years ago, I made the assumption 3 years ago that OpenAI was going to be on the wrong side of history. OpenAI made the wrong play. OpenAI made the wrong play for two specific reasons. One, for closed sourcing their architecture, and then for two, thinking that they could just scale up infinitely via transformers. made a bet against the market and they made a bet against physics. And to me, they lost both of those bets. And that's what we're seeing play out within this in real time overall, right? And then so within that, I've made the opposite bets. I bet on open source and I bet on going hard into physics. And my argumentation and expectation was and is that we've reached ceilings with regards towards computer science, physics overall, etc. If you understand those things and you dive into it, what you can see very specifically is that the only way to make major significant breakthroughs in AI at the moment is via physics breakthroughs. And so that's why I focus so heavily on physics breakthroughs and kind of these crazy experiments, like all like on the fringes. To understand it, like what is the topology of digital spaces, what is the geometry of digital spaces, how exactly do these things work, because these are things that other companies aren't exploring. And then so coincidentally we're the ones coming out with these breakthroughs, right? And then so within this, here's an example of that, right? And then so this experiment was, I just wanted to see what happens if we take quantum entanglement effects and then we replicate them digitally across like different spaces. So for example, if I take one agent, these first experiments are like, if I take one agent in Euclidean space and I connect them very specifically into an agent in hyperbolic space, will the agent in hyperbolic space have any sort of influence and back and forth? And then as we can see, there is there's a phase synchronization that occurs between the two agents within this. So cool overall, right? And then so I just this is just from there more and more interesting experiments where I'm doing I have coupled agents versus no coupled agents, and then in classical versus different geometries, and then with no noise versus high noise, etc. And then interesting patterns emerge from this, right? Just looking at the patterns of data that come out of this, and then kind of the metrics that you get is super cool, right? And then this one especially, these ones, so these are the shapes that the agents are forming on their own, right? These entangled agents, essentially they form this process just by connecting the agents, by simulating a quantum entanglement. The agents do this. Why do they do that? I don't know. I need to explore this better, right? But I'm showcasing to you what exactly and how exactly these experiments come out, and it's just a matter of playing around with these things, right? Playing around with different spaces and different physics than most people would play around with. Most people aren't going to play around with simulating quantum entanglement in a digital system across different geometries. It's just not something that goes through probably the average person's head, right? But then so here you are, and then when you go through this and you see these things, it's these are the physics that come out of it. And you get actual shapes and actual benefits. So how is it that I'm able to, for example, prove out holographic compression and 30% lossless compression here, all of these things, right? 1800% lossy compression. Whatever you want to do regarding compression, contact us. We'll do it for you, and we're looking for one buyer. But so within that, just showcasing overall, it all comes down to physics. I can't say that enough, right? Everyone else is hype train marketing, etc. That's not our play. Our play is 1,000,000% physics, grounded in the physics and mathematics, right? It's kind of the two tracks that we play in very specifically within this, because those are the two areas where actual breakthroughs are going to occur within these things. But end note here, just again, bottom line, if you think that any of this is actually profitable on huge levels, there's not enough market for it. There's a market that the market that understands exactly what I talk about in these videos is very low overall, as a general rule. I think I'm pretty tapping the market that I can tap into within that particular area, and it's smaller than you can see in other niches, right? Just proven out kind of inherently in lots of ways across the board. These are hard things to understand, hard markets to understand. Once you do have someone to understand, it's usually not a person pulling the purse strings that actually understands. And then so all those reasons combined, it just makes it hard to actually make money off of these things, right? And that's like I can't stress that enough. I think there's some people that think like, oh, you make one physics breakthrough, or the massive physics breakthrough, and money will just pour in, recognition will pour in. Name a physicist that's a billionaire or an star. There's none, zero. Like, and then there's reasoning for that, right? And then so here you go. If you like this type of content, please like and subscribe. Thank you very much.